Okay, welcome everybody to this HEP-TN seminar. Today we are very happy to welcome Antoine Tilloy from the Max Planck Institute of Quantum Optics, and he will talk about relativistic continuous matrix product states and promise to present super up-to-date new results. So please take it away.
Okay, thank you very much, Johannes. So I'm very happy to be invited at this series. I think it would be difficult to fit the topic better than with this talk. In a nutshell, what I'm going to present is a variational ansatz to solve a 1+1 dimensional relativistic QFT that doesn't require a discretization or cutoff, and that can solve potentially to arbitrary precision. So it's a sort of, if you like, DMRG for field theory. This is based on two papers. You have a short and a long paper. And they are V1s because I'm currently working on a V2. And since I've presented this V1 in several instances already, and I don't want people to get bored if they have already heard of it, I will also talk about new results that should go into the V2 and that are useful to get this arbitrary precision. So they turned the nice ideas of this paper into something computationally efficient. So these are very, very new results in the sense that I found the algorithm last week and basically crash coded it in Python and started running computations the day before yesterday, so that you have some data points for the talk today. Okay, but let me give you the outline of this presentation. So I will talk about, I will present very basic things about scalar fields in 1+1 dimensions, which is the kind of system I'm targeting that I want to solve. I will explain how it's traditionally solved by discretizing, then talk about an alternative, which is a variational method in the continuum, then mention continuous matrix product states that are the natural tool to apply the variational method in the continuum, but explain that they have limitation in the relativistic case. Then, based on the results of the first point, it's easy to understand how to tune or how to twist this CMPS to fit relativistic theories. So up to there, that's the published results. And there I will mention some recent numerical results that make essentially allow the algorithms to go from a cost in D6 to a cost in D3 that makes it actually usable. And then I'll mention some open research questions related to this. So of course, as usual, feel free to interrupt, criticize while I'm talking. Okay, let me give the basics of relativistic scalar field theory from a condensed matter viewpoint, because that's a viewpoint we naturally use in the tensor network context. The intuitive definition of a scalar field theory is obtained from canonical quantization. It's just a continuum of nearest neighbor coupled anharmonic oscillator. So in the discrete, you have a boson on each side, or an oscillator. It's anharmonic, as the potential doesn't have to be quadratic. You have some stiffness that corresponds to the gradient term. So the oscillators are nearest neighbor coupled, and you have on-site inertia. That's the p-square term of the oscillators. This is a natural way to see a field theory from the condensed matter point of view as local oscillators, local bosonic degrees of freedom. The natural Hilbert space associated to this intuitive definition is just the Hilbert space spanned by the creation operators associated to each local oscillator. And the most general wave function is just the superposition of all the wave function with fixed particle number n, each of them with n excitations over the Fock vacuum associated to these oscillators. That's the intuitive condensed matter definition, and I recall it because that's typically the one we use when we discretize a field theory. So every time we discretize a field theory, usually we use this natural basis. And that's also the one that is natural even for standard continuous matrix product states. However, it turns out that for relativistic theories, so this is a very nice basis for the Liebling-Niger model, for example, for non-relativistic field theory, this local oscillator basis. But it turns out it's not adapted to relativistic field theories. A first simple fact that you notice is that it's not normal ordered in the psi-DAG basis, so you get divergent vacuum contributions. This is, in a way, a stupid divergence that can be removed fairly easily by normal ordering these operators. So every time you see them, you change the order. But if you remove these divergent vacuum terms, then the Hamiltonian is not bounded from below. So you can find sequences of states that have lower and lower energies. So the ground state energy density is infinitely negative. So there is no way to write the ground state in this Hilbert space. So this Hilbert space spanned by the creation operator psi-DAG is not the right Hilbert space of the QFT. But it turns out in 1+1 dimension, at least, there is a fairly easy way to construct a legitimate Hilbert space. And it's to diagonalize the free part first. To do that, you do a Bokol-Lyubov transform. So instead of using this psi-DAG operator, which are local creation annihilation associated to the field phi and its conjugate pi, you go to Fourier space and do a transformation that mixes phi of p and pi of p with a p-dependent coefficient, square root p squared plus m squared. In quantum matter, that's just a Bokol-Lyubov transform. And that diagonalizes the free part of the Hamiltonian. So all the Hamiltonian up to, including all quadratic terms, is diagonalized with this. And now you can just normal order the full Hamiltonian in this operator basis. What that gives you is that the ground state of the free theory is just a vacuum associated to A. So I insist that the free ground state is not the vacuum associated to psi, for example. And the Hamiltonian is then constructed by adding excitations over this free ground state or Fock vacuum associated to A. Turns out, and that's a peculiarity of one dimension, so 1+1 dimension, that this is sufficient to cancel all divergences. So once you do this procedure, you have a perfectly well-defined field theory without any pathological feature. As an example, you can look at 542 theory. So here the 4 stands for the exponent and 2, the number of space-time dimensions. It's a theory given by this Hamiltonian. So it's the same as before, except I look at the simplest anharmonic term. And I normal ordered for the A operator. Okay, so I write all the phi pi in the A basis, in the A dagger basis, and then I normal ordered, and this Hamiltonian is well defined. So it provides a rigorously defined relativistic QFT without cutoff. So it's a legitimate Whiteman QFT. It verifies all the Whiteman axioms. So it doesn't need any cutoff in its definition whatsoever. The vacuum energy density is not 0. So it's finite. It's a number, but it's neither infinite nor 0. It's still very difficult to solve. So it's not a theory that's solved because the fact that we can define it doesn't mean that we can solve it. It's not a CFT. It's not a free theory. And it has a phase transition in a domain that is impossible or extremely difficult to access with perturbation theory. So if you fix the mass to 1, and then for G equal roughly 2.7 in mass units, you have a phase transition. In the discrete, so for discretization, usually people use these units. And actually, people, myself included, use this unit where the phase transition is roughly at 11, so at 4 times this phase transition. Just a matter of units. Okay, and so a good, since this theory can be so easily well defined, but hard to solve, the question is, but how do you solve it? And let me mention first the most standard way that we have all been doing in this field. Okay, now before that, let me just summarize what we've learned so far on basics of scalar QFT. is that you have a natural basis from the condensed matter point of view. That's the psi-dag of X basis. What's nice is that it's local in the field. So in particular, the Hamiltonian is also local in this basis. It's very natural for discretization as a result, but it turns out to be divergent and ill-defined. However, the AK basis, the basis that diagonalizes the free part, it's, if you like, it's probably badly named, but it's sort of the relativistic oscillator basis. It's non-local with respect to the field. It's clearly less natural for discretization, but it's regular and well-defined. So this is a lesson we will use later to correct the issues with CMPS in the relativistic context. Okay, if there are no questions at this stage, I will go on and explain how, recall the very basics of how people typically solve this theory. So the standard way.
Can I ask you a question?
Yes, sure. Yeah.
You said we don't need any cutoff in this theory, but how about loop? UV divergence come from loops.
Yeah, so the normal ordering removes all tadpole diagrams, so there is no divergence. The loop orders are finite.
So it's different from usual pi-4 theory.
No. Phi-4 theory has tadpole divergences. Renormalized Phi-4 theory is what you get when you kill the tadpoles, and killing the tadpole is equivalent to normal ordering. Maybe what you have in mind is Phi-4 in more dimensions. So in 2+1 or 3+1, where you have more diagrams that are divergent, like the sunset diagram, and there normal ordering is not sufficient. But it turns out that in 1+1 dimension, for bosonic theories, it's generic that normal ordering is sufficient.
Oh, I see. So
this is a dimensional.
1+1 dimension.
This is proper to 1+1. Yeah.
Do you have? Is there any generalization to a higher dimensional case in your setup?
Of what I'm going to say today, so far, no. Of rigorous construction of field theories, yes, to 2+1. 2+1 is still rigorously well defined. It's just the picture is more complicated.
Okay, thank you.
And 3+1, as you may know, doesn't exist. So 3+1 scalar fields have been shown very recently to be ill-defined by Eisenman and Dumil-Copin. So it's a Phi-4 theory is the one you see in textbooks. It's perturbatively renormalizable, but it's not a true quantum field theory, essentially because it's not asymptotically free. But yeah, that's another story. I will stay in a very simple context of 1+1 dimensional field theories where bosonic theories are generically well defined by normal ordering. So that's also true, for example, of sine-Gordon, cinch-Gordon. All these models are well defined, at least for some values of the coupling with normal ordering. Okay, so if that's okay, I just keep on. We will see actually the divergence in a different way here. So the standard way is you discretize. So here I'm looking at because of personal taste, but you could do it also in the Hamiltonian way. I'm looking at it in the Euclidean way by discretizing the action. So the gradient square term becomes a finite difference, and then you have a mass term and the quartic term. And you write this on the theory on the lattice, and you try to solve it on the lattice, for example, with tensor networks. But you can also do Monte Carlo or any other method you like. There, the right way of taking the continuum limit, it's a dangerous notation. A is just the lattice spacing here. It's not the creation operator. You just rescale the mass with its dimension, the coupling with its natural engineering dimension, but you have a logarithmic correction. And this logarithmic correction is exactly the normal ordering term, and it's exactly equivalent to tadpole constellation. And intuitively, what that means is that at first order in perturbation theory, the Phi-4 term behaves like a huge mass that diverges logarithmically. So you have to cancel this huge mass to make the theory with a finite interaction and finite mass. Okay, So that's lattice phi 4. You define it on the lattice. I give as a very biased example, we did it last year with Clément Delcamp at MPQ. We just did exactly what I said. We discretized it like many other people. Okay, I'm not claiming we were the first to do that, not at all. We discretized it with the action above, and then we used a powerful tensor network algorithm that was TRG plus GILT. So graph-independent local truncations to solve the theory, so to compute whatever you want to compute with it. But we could have used the boundary MPS. So any theory you have to solve a 1+1 discretized now dimension system. And what you can do is then you take the continuum limit numerically. So here lambda is a proxy for the lattice spacing. Okay, we just take the in the lattice theory, taking the coupling to 0 is equivalent to taking the continuum limit. And what you see is that our error bars explode as we get closer to the continuum limit. So we have to do a fit, an extrapolation to get physical quantities in the limit. So here I'm looking at the critical coupling, but that would be true for any other quantity I want to look at. The error, the tensor network algorithm or Monte Carlo algorithm is gonna explode when you go to the limit. Why is that? Basically because the fields become unbounded at short distances. And so you need a huge starting bond dimension. In the MPS language, you need a huge physical dimension when you start, when you want to discretize the field theory in a finer and finer way. It turns out that for our algorithm, there is an additional error that comes from the fact that we have to do more RG steps to get to the same scale if we start from something smaller, but that's not an issue you would get with boundary MPS, for example. So I insist that's really the fact that that there is an issue when you discretize a lot.
Sorry,
Let me, yes.
Hello. Where does the error come from? So typically in the tensor network, you don't have any error, right? So do you run it?
Yeah, so it's bootstrapped. You're right. These bars are heuristic. Okay.
Okay.
Basically, we take a large bond dimension limit and see that the final result still fluctuates when we take the bond dimension to infinity.
Okay, thanks.
Also, I mean, it's not technically infinity here. It's 120, I think, or TRG bond dimension. So we try to estimate the error, but we see that clearly it increases. But it's true for all tensor network methods. Usually you can say, yeah, but it's expensive to take this numerical limit, perhaps because we take the wrong local basis choice. You know, often if you take the wrong basis choice locally, it looks huge, but maybe a small local rotation would bring you to something that's small. That's not the case. The problem is spectral. So at short distance, a field theory, so these types of theories are free conformal field theory. So they have a continuum of singular values. So when you go to the continuum limit, your initial tensor has to encode a continuum of singular values. On the other hand, the interaction is super-renormalizable. Okay, that's why it's super-renormalizable. So that means it's strongly relevant, which means if you look at it the other way around, it goes to 0 if you look at it at short distances. So when you go to the continuum limit, the closer you get to the continuum limit, the more the free part takes all the singular value, a continuum. And on the other hand, the interaction becomes an epsilon-esque, a tiny perturbation of this tensor made of a continuum of singular values. So if you go too far down the continuum limit, the interaction is washed. Like you would have to work with 10⁻16 precision at every RG steps to keep track of the interaction. It's completely theory independent. That would also apply to QCD. So that would apply to all quantum field theories that are asymptotically free, and thus that have a negligible interaction at short distance. This issue. That doesn't mean you cannot make computations. It turns out so far the lattice computations are the most accurate for infrared properties. You can look at, so this critical coupling, here you have estimations that were given with tensor cos graining, MPS, Monte Carlo, and so the GIL TNR we did with Clément, you see that the precision is fairly good and is in fact slightly better than Borel resummation and renormalized Hamilton truncation, that are methods that work directly in the continuum. And very recently, our friends in Ghent have finally crushed us with using matrix per X states, finite entanglement scaling, and continuum scaling in a more data-driven way to find an even better estimation of the critical coupling. But these methods are really based on extrapolations. So we know we cannot go too far in the continuum limit because the short distance behavior is a CFT, and these states are not well made for that. And so we extrapolate, and in these papers, the extrapolations are really exceptionally good. So the results are much better. Actually, I talk about this on my blog about this paper and this idea, if you're interested. But now I would like to do a different way. So really do the genuine continuum limit, not have to do extrapolations, at least as far as the short distance behavior is concerned. So let me go explain quickly the variational method. So we are very familiar to it. That's the idea of tensor networks in a way, that we want to find a submanifold of the Hilbert space and just find the ground. Yes.
I have a question, Antoine.
Yes. Sure.
So you're basically saying that, like, even if your interaction induces some bound states, like this method is not going to be able to sort of detect them, or like it's going to be very hard to see them.
I mean, on a fixed discretization, it's always going to work, but I'm saying that all the theories we know. So this, what I say, is probably not valid for perturbations of non-trivial CFTs, for example. I will talk about this more at the end. But if for most QFTs that appear in high energy physics, like QCD, they are free at short distance.
Yeah.
So that's generic for these theories. If you look at a perturbation of Ising CFT, maybe there is a way, but I don't know. Okay, that's another story.
Okay, thanks.
Okay, just so, I mean, it's an audience mostly familiar with tensor networks, but I think it's good to know that this variational method is implemented by Hamiltonian truncation. So it's a method that's also popular in high energy physics, in that you put an infrared cutoff such that the momenta become discrete, and as submanifold, you take a Hilbert space. So it's not really, so it's a trivial manifold in a way. It has a linear structure. The vector space spanned by a finite number of creation operators, and you put a cutoff in momenta. So you say the momenta cannot be larger than this. So usually they do a cutoff in energy, but to simplify it, I said momenta here. And let's say you also fix a number, okay? And this gives you a variational method that works directly in the continuum. But that's not tensor networks. Okay, more generally, for relativistic field theories, there are a series of objections, or it's at the same time requirements and objections by Feynman that say what a good ansatz would look like. The first we are extremely familiar with is that we would like an ansatz that is extensive, so that the number of parameters to parameterize our state doesn't grow exponentially as the system size. Okay, like it does typically, but grows at most, say, linearly, or in the translation invariant case, maybe doesn't even grow with the system size for gapped systems. You see that Hamiltonian truncation breaks this already. So Hamiltonian truncation has an exponential cost in the system size. The second thing is that you have to have computable expectation values. So if I give you the state, you have to be able to compute, for example, 2-point functions, or even just the energy, so that you can minimize the energy with the variational method. That's highly non-trivial. So in QFT, if I give you a wave function, in general, it's totally impossible to compute correlation functions, because the wave function contains infinitely many coefficients. So even if you have a sparse parameterization of those coefficients, it doesn't follow that you can compute correlation functions. And also, it should not be oversensitive to the UV. And that's a bit related to the fact that QFT are ill-defined in the psi, in the local oscillator basis. That is, if you minimize an energy that's divergent, what's going to happen is that all the coefficients, all the free parameters of your variational ansatz are going to be used to fit this high momenta. And that's something Feynman observed himself. So he was toying with some variational wave function and seeing that as he optimized the parameters, I don't know how he did that, the approximations were getting worse. So far, all the methods on the market, they break at least once. So Hamiltonian truncation, which is very popular in high energy physics, breaks one. And tensor networks, as we well know, they succeed at 1 and 2, at least for MPS. So for 1 + 1, we have efficient way to compute correlation functions. But they fail a priori at 3. So I will explain why they fail at 3. Maybe it's not so obvious. So this is in what follows. Of course, my objective and the novelty of the method I present is that it fits all 3. And as far as I know, that's the first time that one can fit all 3. Okay, no, I should be more precise. Actually, Gaussian states fit these 3, but we would like an ansatz that is arbitrarily expressive, that can reach in principle arbitrary precision. So the ansatz I propose, as far as I know, is the first one that does those 3 and that has arbitrary precision. Okay, the first step is to look at matrix product states. So they will fail at 3, but they are the starting point for my construction. Okay, usually I spend a lot of time explaining how you derive them from MPS. It turns out it's almost always a failure. So I will just directly give the definition. Okay. And then you can accept or get the intuition that it comes from MPS or not, but I think it's easier this way. Okay, so CMPS are states for non-relativistic, or maybe at the time, probably they didn't know, maybe even relativistic QFT. That was introduced in 2010 by Franck Verstraete and Ignacio Sirac. It's like an MPS, it's a state that is parametrized by here 2 matrices of size big D by big D. And given by the trace of a path order exponential of an integral of this matrix tensor the identity and the psi dagger acting in the field theory Hilbert space. Here it's the fog vacuum of the field theory Hilbert space. So you can really think of either the Liebling-Niger model or the naive 5-4 definition I gave before the renormalization, ignoring for now the divergences. So inside the exponential, you have an operator acting in the tensor product of this matrix Hilbert space and the field theory Hilbert space. When you take the trace, it's something acting in the field theory Hilbert space. So the final object is indeed something acting in the field theory Hilbert space. Okay. So the intuition is that it's really a continuum. It's a genuine continuum limit of an MPS. So, but it's so the path ordered exponential is equivalent to having an infinite product of matrices that are very close to the identity. That's as far as I can go in the explanation. But if you know even nothing of tensor networks and just come from a QFT background, this is a sort of non-commutative coherent state. So if Q and R were complex numbers, this would be a coherent state, a field coherent state. And so I'm saying that now if I don't put numbers, I allow myself matrices. So it's sort of a generalization of coherent states. The huge advantage of putting matrices here is that now these states are dense in Fock space. Okay, so the state of this form Q and R, okay, if Q and R are X dependent, span all states in the QFT Fock space. And if they are non-dependent on X, as I wrote here, they are dense in the translation invariant states. So you get all the states. Of course, I'm not saying you get that. We don't know if you get them efficiently. From the intuition of MPS, you expect that you do. Numerically, people see that you do. But as far as I know, there is no proof. If this definition is clear, I will proceed. But if not, feel free to interrupt me. So okay, I should just before going to the next thing, you see that it fits very nicely the first of Feynman's requirement, that is the parametrization of the state is extensive at most. So if it's translation invariant, we have a fixed number of parameters, QR. If the state is not translation invariant, then the number of parameters grows linearly with the size. The second point is that just like for MPS, you can compute all correlation function efficiently as simple matrix expressions depending on R and Q. So R and Q parameterize the state, and all correlation functions have compact expressions. So you have to introduce a transfer matrix T that has this form that's equivalent really to the transfer matrix in the MPS case. And all correlation functions have a simple form as a function. Of course, the expression even further simplifying the thermodynamic limit. When L goes to infinity, this becomes a projector. And so the expressions even further simplify. But just, it doesn't really matter here. What matters is that it can be done. So if you give me a CMPS, you give me whatever correlation functions, I can compute it with a Python code that's going to run in 1 millisecond, or maybe, say at most 1 second for large quantum dimensions. And for example, it's been applied in the original paper on the Lieb-Liniger Hamiltonian, which turns out to be exactly solvable, but you could consider non-integrable perturbations. And they just solved it by minimizing the energy, in fact, rather the energy density. So you just have the energy density depends on Q and R, these two matrices, and you put that in whatever solver and you minimize it. And they went to bond dimension 8, I think, back then. And it gave a fairly good approximation. I think, unfortunately, from this original bond dimension that was rather low, because it was a first test, people concluded that CMPS are not efficient, but it's not true. In fact, CMPS are very efficient. So in 2016, Ganal, Rincon, and Vidal, they did computations with bond dimension 256. For the Lieb-Liniger model, you reach essentially machine precision with this bond dimension. So close to machine precision, I think. And recently, there is a paper from our Ghent colleagues that also gets closer to the margins and that you can do open boundary conditions efficiently as well. So it's not such a fringe method. It works for non-relativistic field theory, and it's competitive. Of course, the issue is that it's non-relativistic, and I don't know, personally, but I find these non-relativistic field theories like Lieb-Liniger and stuff less interesting than the relativistic ones, in a sense because they don't have any of the difficulties of difficult QFT, which typically difficult quantum field theories are not particle conserving, they are divergent at short distance and stuff, all things that these non-relativistic QFTs don't have. Of course, very early on, people tried applying this ansatz, this continuous matrix product states, to relativistic field theories. And you can do it for example, I just give as example the phi-4 Hamiltonian, and you realize instantly that the energy density is infinite. Okay, it's divergent for the very reason I explained first. Okay. So the short distance, and this is because the short distance behavior of the CMPF is wrong. So for a state defined this, sorry, let me stay here. The short distance of a CMPS is regular. So if you look at a phi, a two-point function of the field, it is necessarily regular at short distance, whereas we know that relativistic field theories are conformal field theories at short distance. So they have to be divergent. The fix, it's actually a very neat fix that was done in 2010 to still deal with relativistic theories, was to add a non-relativistic cutoff in the Hamiltonian and then solve the theory with CMPS still. So that works, but that changes the problem. Okay, now we are no longer solving the true Hamiltonian, we are solving a regularized version of it. So it's neat, and it's a very nice toy model because it gives you a nice way to understand what happens when you take the relativistic limit of a non-relativistic theory. But on the other hand, it defeats a bit the purpose of going to the continuum limit in the first place, because if we go to the continuum and then regularize again, I mean, we could as well go to the lattice directly. So I would like to use CMPS, but without regulating anything. So to go relativistic, the idea is to learn the lessons from the very first part of this talk about scalar field theory. And at the beginning, I explained that this local basis is nice from the condensed matter point of view, and to discretize this psi-dag basis related to the fields. But the diagonal basis of the free parts, AK dag, is the right one in terms of Hilbert space to have a convergent, to have a well-defined Hamiltonian. And this is the Bogoliubov transform that relates this psi-dag and to actually the fields and the A of P. So this is a much better starting vacuum than this one. So the idea is to start the CMPS not from this vacuum, but from this vacuum, the vacuum that is already taking care of the divergent free parts. Then we could use the A of P directly. The issue is that physics is not translation invariant in momentum. So we need an operator in space. We need an operator that lives in space. Further, we need an operator that has the same commutation relation as psi of x. So we need something that commutes, that has canonical commutation relation with its dagger, like standard creation annihilation operators. The only way to do it is to take the Fourier transform of A of P. This way you will be in the right Hilbert space, you will have the right commutation relations, and you will be living in space. Okay, I insist because I actually got quite, only criticisms I got on this ansatz was that that looks non-relativistic. And that's true. So this prescription is not covariant, is not anything. My point, as I will explain below, is that it doesn't matter. In fact, we cannot hope for better than that. So with this, for me, a relativistic CMPS is just the same as a CMPS, but here I change the operator. I take A dagger of x, the Fourier transform of the creation operator that diagonalizes the free part, and I act on the fog vacuum that is also the ground state of the quadratic part of the theory.
So sorry, can
Yes.
I have a question?
Sure.
So I'm not sure I got everything. So like you said that previously there were applications of this framework to maybe free quantum field theory, right? Like with this additional term in the Hamiltonian, I think like that was partially identified.
This?
Yeah. So what was used in this work as a field theory operator in the ansatz? Like, was it phi, like the relativistic phi?
No. So this, when you do this modification of the Hamiltonian, it's to use the standard CMPS. So you have psi-dag psi, where psi-dag, sorry, I think I wrote it just above, sorry. So the field is related to psi and psi-dag this way.
Okay, good.
So the field is the X, if you want, where this is, yeah. So this is a non-relativistic prescription.
Good. So your point once again is to use like the analog of psi, but for a relativistic system, right?
Yes, exactly. Exactly.
So like you have like the field. So basically, when you have like the free field operator for a boson, right? Like it consists of this guy plus a dagger, right?
So the only difficulty, so here, this is totally not the field operator because there are these omega p factors and I'm not—
Oh, so omega p you ignore. Okay.
Yeah, there is no omega p, and that's crucial because otherwise A of x would not commute. So you need, so you have two things you try to do. So you want relativistic invariance, but I will explain that it's lost anyway, whatever you do. And then you want commutation relations to be correct. So you want this to commute with itself and to have canonical commutation with its dagger, because otherwise you cannot compute expectation values.
Oh, okay. Because in the, can I just, yeah. So in the relativistic system, you would have here like 1 over square root of omega or something.
Exactly.
Right?
Exactly.
So, yeah. And if you have it, then like a dagger, like A of x, a dagger of y, like would not have nice commutation relations.
No, they would not.
Oh, I see.
Yeah.
Thanks.
So I agree. So many people suggested that it would be a much better choice, but it's a choice that look aesthetically nice, but then you cannot do anything with it.
But and you make this choice because you just want to use like the thing that worked for the non-relativistic system and just apply it to the relativistic Hamiltonian.
Yes, and also this is the only way I know how to compute expectation values. So if I have these computation relations, they are really required for, so basically they encode a form of locality in the state. And so without it, it's not possible to compute correlation functions. So to compute the energy even. So I will just,
so this is very, so when there is a, let's see, so when like there, well, I mean, it looks like a field, like part of the field operator for the Hamiltonian whose ground state is like the reference state in simera, right? Like in simera.
So actually, I'm moving away from that. So this really corresponds to the reference state in simera.
Yeah.
And I think it's a bad choice, to be honest. So I think the issue is that this state has clearly non-relativistic behavior.
Yeah.
So I would like a reference state that has a relativistic behavior in the first place. So when I say relativistic, not necessarily covariant, because this is lost in the interacting theory, but that has the right short distance CFT behavior. So this is a CFT at short distance. So if
so you want A of P to create like a particle of a CFT, to annihilate the particle of a CFT, or like of a
no, so not a CFT, a massive free theory.
Massive free theory, good.
But it's just at short distance you don't see the mass. So
yeah, sure. I see. I think I see what you do.
Okay, no problem. You feel free to ask more. So just to summarize the properties, so what is neat with this state is that if you take R and Q equals 0, which in a way corresponds to bond dimension 0, you already have the ground state of the free part. So this is the exact ground state of the free part. But because the interaction is super-renormalizable, that's also the same as the interacting ground state at short distance. So you have captured the short distance behavior even of the interacting theory exactly. And that's why you don't get into the worry of Feynman.
So the vacuum A, like that you have here on the right-hand side, is the vacuum of a free boson.
Yes, of the
relativistic free boson.
Yes.
Okay.
But when my point is that for super-renormalizable interactions, which is essentially all bosonic interactions you can think of in 1+1 dimension, at short distance, this state is undistinguishable from the interacting ground state.
Yeah, sure, I understand.
Just at short distance, of course. And what you can show, this is not obvious, you have to carry the computation, but that if you look at the Hamiltonian density, its expectation value is finite, whatever the value of Q and R. I insist again that A of X is not covariant. It doesn't have nice transformation properties, but that doesn't matter because the state cannot be exactly Poincare invariant anyway, because we are acting on the free vacuum. And if we could target an exactly Poincare invariant state directly, we would have solved the problem because there is just a true ground state that has this property. So these properties asking for strong covariance or Poincare invariance in a variational method, it's not possible anyway. So since this is wasted, at least let's take an A of X that has the right properties for us to make computations. Okay, that's the point. Now I will go to the main cost, the main drawback of the approach that first makes you think it's completely doomed. Okay, the thing is the Hamiltonian is local in the field operators and thus it's local in psi, but it's not at all local in A of X, especially because of these square root omega p factors that are missing. So now the free part, instead of being a simple integral of a density, the free part is a double integral. And for example, the quadratic part is a quadruple integral. And if you had a phi 6 term, it would be a 6 integrals. Fortunately, these kernels, they depend on Fourier transform of 1 over omega p, basically. And so they decay exponentially with distance. So this Hamiltonian is not local, but it's sort of weakly local. So beyond the mass scale, it's local. Okay, so at least conceptually, the CMPS should still work very well for such a Hamiltonian. So here I'm just rewriting the usual Hamiltonian of the relativistic field theory in this new basis so that I can apply standard CMPS techniques. So what is the procedure? I compute the energy, I compute the gradient, and then I minimize the energy with, the best method is to use TDVP, so the time-dependent variational principle, which is essentially gradient descent with an optimal metric. Now the computations of the energy and the gradient contain two parts. The first part is algebraic, and it's identical to standard CMPS. So I have to compute expectation value of A dag of X, A of X, for example. The second part is, once I know these expectation values, I have to integrate them. Okay, it's not just, I don't need them at a single point, I need them at integrals of points. My initial idea, which is in the papers published, so not published actually, so on arXiv so far, was to brute force all these integrals with QuadPack numerically. Okay, so that works. That was, I should say, tremendously difficult. And let me show the first results you get with this very naive approach of computing the expectation values. So the first results I did was look at the energy density and comparing with the best continuum method, which is renormalized Hamiltonian truncation. And there you see, so I could only reach moderate values of the bond dimension. That's already very competitive, and at large coupling, it's even better than renormalized Hamiltonian truncation. You know it's better because the method is variational. So if you are lower, you know you're closer to the true energy. These points are rigorous in a way. You know that the true energy density is necessarily lower. So they give rigorous inequalities. Usually it's not rigorous because we are using extrapolations, we are working on the lattice, taking a continuum limit numerically. Here, since it's directly in the continuum without any cutoff, these are genuine variational results. And then I used extremely high precision results from renormalized Hamiltonian truncation that were found in 2017 by Rychkov and Vitaly Eliasmiro, where they pushed it a lot for two values of the coupling. And for these values, it was more precise than my own results. So I could sort of try to guess the convergence. And yeah, and I think there people were happy, except my referees who said, yeah, it's not good. A method that has 1% precision is useless. So I was a bit bummed, but I kept on. And I tried to argue that at least the scaling is better asymptotically. Okay, so if you look at the standard method of Hamiltonian truncation that I presented briefly first, this method has a number of parameters. That's a cost that is exponential in the infrared cutoff and the energy cutoff, while the error you make decreases as a power law in the cutoff. Here, we have a number of parameters that is proportional only to d squared bond dimension, and an error that is believed to be super polynomial, if not exponential in the bond dimension. So that's proved on the lattice. That's proved on the lattice and suggested by this plot, but you will see that I could do much better recently. Okay, so that was the status. We have a method that is promising because its scaling is clearly much better than anything that exists. And it's directly in the continuum, so there is no need for any extrapolation. On the other hand, because of this very expensive computation of integral with QuadPack, I was limited to low bond dimension. So this is now that we switch from stuff that's on arXiv to, in a way, bleeding edge results that date from last week. Okay, so I did that stuff last week. This way you get something fully new and you didn't go to the talk for nothing. I was trying, in fact, to solve with this method, I was trying to solve the Cinch-Gordon model. In the Cinch-Gordon model, you have expectation values that are exponential of the fields. If you expand it, that gives you a sum of integrals and of nested integrals. And so if you expand it up to degree n, you have n nested integrals. So it's a nightmare. But it turns out I discovered that, in fact, these terms are easy to compute. They have a cost only cubic in the bond dimension if you solve it as an ordinary differential equation. So the way to do it is you write the field as a function of A of X. Okay, then you realize that this normal order expectation value takes this form. And in fact, this form is just a generating functional. That's just by definition, that's how we define the generating functional in the CMPS case. Here, the source in the generating functional is the Fourier transform of this omega p, 1 over square root omega p term that's problematic. So at the end of the day, the expectation value of a vertex operator of this kind is just equivalent to the generating functional for a fixed source. So you just have, if you can compute this for whatever source, you can compute vertex operators very efficiently without ever computing an integral. It's just an ordinary differential equation. How do you do it in practice? So you do the usual trick of going from the transfer matrix to the Lindblad operator picture, which you do by going in, I think it's called the left canonical gauge. But this generating functional is equal to the trace of the solution of this ordinary differential equation. That's an ordinary differential equation over matrices of size d by d. And so its cost, the cost of applying these operations is d cubed. So you have to compute the solution of an ordinary differential equation where the derivative term has a cost d cubed. And this is doable efficiently, for example, with Runge-Kutta, with whatever. I'm using a Steve BDF solver, but whatever method you want is going to work. Okay, that was actually very good for Cinch-Gordon, Sine-Gordon, these new theories I wanted to study. But I realized, in fact, you can compute all other expectation values, for example, phi4, by just taking derivatives with respect to b. Okay, so if you take derivatives of a vertex operator and take b equals 0, that gives you powers of the field. So what you can do is set up, so you don't actually compute that and then take the derivative. You just look at, you take the derivative with respect to b of these differential equations. That gives you a new differential equation, which you can solve as well very efficiently against as a cost d cubed. So when you're there, it costs d cubed to compute expectation value, but you have d square parameters, so it's going to cost you d5 to compute the gradient. But you can be smart, which I was not before because I first tried with the computation in d5, that you can compute the gradient at the same cost by solving the adjoint differential equation. So I have no time to explain this here, but essentially you do backpropagation for those who are familiar with machine learning. And with backpropagation, you can compute the energy with exactly the same cost as the gradient. So although the gradient has d squared components, it comes from the exact same cost as the energy. Bottom line is that with a cost proportional to d cubed, you can solve all theories with a potential that is polynomial in phi. So for example, all normal ordered expressions of the field, monomials in the field, but also all exponentials. So that includes Sine-Gordon, Cinch-Gordon theories. And also you get, I don't know if you get them all, but you get a lot of fermionic theories via bosonization. For example, you get the steering model just from the bosonic side. What would be interesting is also to try to write the framework directly in the fermionic context, but I mean, you already have, you can already solve fermionic theories with this approach, some fermionic theories at least. Okay, so basically I discovered this last Thursday, exactly a week ago. Then I coded it in Python. I finished about 2 days ago. And I started running first results. So please be kind because the results are not amazing yet because I didn't have much time just to run that stuff on the cluster. It's coded in plain Python, nothing is parallelized, nothing is optimized. So these are the results for the relative error as a function of the bond dimension. So yeah, you see that we go much better. Now it turns out that the renormalized Hamiltonian truncation results are not precise enough. So I take as approximate exact value, I extrapolate, I computed results 1 at bond dimension 25 and extrapolated. Okay, so that gives you a good estimate of the error. every time you add 7 to the bond dimension, you divide the error by 10, roughly. So at 25, the error is expected to be 10 times less than the error at 18. Essentially, the cost is only in d cubed. So right now it's not super stable, but you can potentially push it to more than 40 of bond dimension, in which case the error is going to be, it's going to be as low as you like, basically. I had some time to compute. So once you have the state, all expectation values, they come for free. They are easy to compute. It's not like for Monte Carlo where you have to rerun a Monte Carlo for each observable. So here, if I looked at magnetization, for example, some points near criticality are missing because at criticality, the optimizer becomes slower, and thus I didn't have time in the last 2 days to run them on the cluster. But honestly, they are running right now. So tonight I will have all the points at bond dimension 20 and 15. The last point I put them 20 minutes before this talk. And so you see clearly the phase transition, and that we are closer to the true phase transition at large bond dimension. Away from criticality, it's exact. I mean, of course, you get slightly more precise by increasing the bond dimension, but the physics is essentially the same. As you get to the phase transition, I mean, it's still fairly precise for something that's just next to the phase transition, but you converge uniformly to the right curve that we expect. Of course, I looked at the magnetization, but you can look at whatever. So for fun, I just look at phi 3. It's one click. I just change the n from 1 to 3. You can also look at vertex operators. So vertex, for example, cosh phi. This is the expectation value of cosh phi as a function of the bond dimension for various coupling. I mean, once you have the states, you can compute everything. Everything is cheap. Okay, these plots take basically 1 minute to show up. So once you have computed the ground states at each bond dimension, each coupling, these plots take less than 1 minute to show. Okay, that's for the numerical results. And as promised, I want also to mention, maybe in case you're interested, so 4 open problems or perspectives that I think are naturally opened by this research. The first is that clearly this ansatz points to a new definition. I'm not saying it's better, it's a different definition of entanglement entropy. Because for the notion of space locality induced by A of X, okay, you can look at the Hilbert space as a tensor product of vector spaces spanned by these A of X instead of the usual phi of X. I believe that gapped QFT ground state verifies the area law with a finite prefactor in this basis. So that entanglement entropy is finite in this basis. So it's weird from a relativistic point of view because this notion of locality doesn't coincide with the standard notion of causality in a relativistic QFT, but it captures what we want. I mean, we don't care about entanglement entropy because of causality. We care about entanglement entropy, at least in the context of tensor networks, because it gives the right notion of approximability. And here, the fact that we get extremely good approximability with finite bond dimension without cutoff clearly suggests that this entanglement entropy must be finite, but I don't even know if this conjecture is true. And I don't know if it's a useful notion, this entanglement entropy, but that's open. Maybe the answer is trivial. I've just not given it more thought. Quickly, another problem that's difficult, I think, but that's open, is that right now I'm having a short distance behavior that of a free CFT. Okay, it's a free boson at short distance. That's something that's fairly generic, I think, in high energy physics, in the quantum field theories that occur as fundamental theories of nature. But it would also be interesting to deal with relevant perturbation of other UV CFTs. So you can take the Ising CFT, not as an infrared CFT, but as a UV CFT, and look at the perturbations. I know this is something people find very interesting in the CFT community, but I don't know how to construct an ansatz in this context. You have to find the equivalent of A of X for a more generic CFT, sorry. Perhaps one can use a Coulomb gas construction to get back to something Gaussian or that looks Gaussian, and then I don't know. That's very open. I think that's another good question. Another thing that could be interesting, I think, is to construct, based on this, a relativistic simera. So a simera that is, the standard mera is a trivial theory at short distance and a critical theory at large distance. That's not the standard behavior you have in QFT. In a relativistic critical QFT, you have a CFT at short distance and another different CFT at large distance. And I think it would be interesting to try to find states, ansatz, that are a bit of a mix between simera and relativistic CMPS that have this behavior. So of having a certain singular behavior at short distance and a different singular behavior at large distance. And that would be adapted to critical QFT. For example, you could use it for 5-4 theory exactly at the critical point. Because this theory is the free boson, central charge 1 at short distance, and the Ising CFT, central charge 1/2 at large distance. Finally, last point, and a bit the elephant in the room, is to go to higher dimension. I should say this is still very difficult. So I find it very interesting, but that's an active and a long-term goal. The first is there are two difficulties to go to higher dimensions. The first is related to relativistic quantum field theory. Normal ordering and tadpole or equivalent tadpole constellations are not sufficient in more dimensions to kill all divergences. From Whiteman, that Whiteman QFTs still have a Hilbert space. They still have a legitimate Hilbert space construction, but it's very non-explicit. Essentially, they require solving the theory exactly, usually. And it is certainly not the free Fock space. So you cannot write rigorously the Hamiltonian of a Whiteman QFT in more than 1+1 dimension in the free Fock space. So that's a difficulty right now that I don't exactly know how to bypass. The second difficulty is related to tensor networks. And it's that continuous versions of tensor networks, so the equivalent of MPS, but in 2+1 dimensions or 3+1, are much less developed. 2 or 3 years ago, I think, we made a proposal with Ignacio, which is to promote the RNQ matrix to fields. And we more or less argue that this is inevitable to preserve Euclidean invariance. I think these arguments are convincing, so I stand by them today. We tested this ansatz on Gaussian problem with Teresa, who was doing our master's with me at MPQ. And it was also tested independently in Ghent by Bastian Albrecht, who was also doing his master's on the subject. And we saw that it works very well. So it's a good ansatz, it approximates well, but so far it's known how to compute correlation functions exactly only in the Gaussian case. Beyond the Gaussian case, you have to solve a boundary 1+1 dimensional relativistic quantum field theory just to compute expectation values. And this is why this talk helps, because you can solve it using relativistic CMPS. Okay, so you can use the tool of this talk to compute expectation values of non-relativistic tensor networks in 2+1. So the non-relativistic 2+1 case now seems barely feasible thanks to RCMPS. It's still non-relativistic, so I'm still not doing the modification to make it relativistic. And of course, I'm not solving the RQFT problem of more than one dimension. So it's really an open problem right now, and that's the state of the field now. Okay, so that's all for these 4 open problems. I just summarized. So I presented a new ansatz for 1+1 relativistic QFT that works, I think, for all reasonable 1+1 relativistic QFT, except perturbations of non-trivial CFTs, but I think they are more fringe. The ansatz has no cutoff, UV or infrared. Okay, so it works in the thermodynamic limit, and there is no energy or momentum cutoff or lattice cutoff. The trick and the main idea is to capture the UV behavior exactly at bond dimension 0, essentially. So you start from a state that already has in it the exact UV behavior, so that the free parameters are used only to deal with the infrared. The method is efficient, so the cost is polynomial in D, in fact D cube. And the error from theory, from the rigorous results on MPS, you believe it's super polynomial in 1/d at least. I think the numerics suggest it's even exponential with an error divided by, so with an energy error roughly divided by 10 every time you add 7 to the bond dimension. And because of that and the new algorithms I presented that scales at d cube, I think it's even competitive now. So at first I thought it was just a neat idea. Now I think it can essentially become the most efficient method for 1 + 1 problem. I mean, that's maybe not at criticality, because at criticality, you don't really care about the short distance behavior, but you want very large bond dimension to take care of large distances. So there probably it fails, but I would say deep in the phase, if for massive QFT, it's probably now the most efficient. I have actually presented results for 5.4, but I'm already running results. I'm already running numerics for Cinch Gordon on my computer, and it seems to agree fairly well with the better ansatz results. And finally, I think a point that's important and that motivates a lot why I went to the continuum limit in the first place is that the results are to some extent rigorous in the sense that they are variational. So you know when you find an energy that the true energy is lower. And if you find a new state at larger bond dimension that has a lower energy than the previous state, you know that it is a better approximation of the ground state. Its overlap with the ground state is larger. And this, I think, is very important because that shows that makes the result very robust. So we know that we get better as the bond dimension increases, and we know that indeed we are converging to the ground state. Okay, so I conclude here. Thank you very much for your attention.
Yes, thanks for the talk. I just have a quick questions. Maybe you've discussed before. So I wonder how is this relativistic QFT Hamiltonian you discussed different or compared to the standard Covey-Susskind Hamiltonians? Is the Covey-Susskind formulation in the continuum limit also relativistic or not?
So you mean that's another open question, how to deal with gauge theories, and that I don't know. I have not tried to do gauge theories.
Okay,
but it's a very good point. So it's probably the next. I should have mentioned it in the open problem. So one of the open problems is to, for example, deal with the Schwinger model without tricks, so without redefining, without eliminating the gauge fields, would be very interesting. But a priori, I see no issue. Like the standard constructions people did should follow through. But I'm not knowledgeable at all on this, so I should. Yeah.
But I just wonder, for example, if in the next step we want to deal with this relativistic gauge series, like QED in higher dimensions. How is this relativistic QFT Hamiltonian you mentioned different compared to maybe the existing Covey-Susskind formulations people usually do? Or anything you have in mind?
I'm not sure I get the question. So the relativistic, yeah.
Right, so I think in the standard literature, there people also do like Covey-Susskind formulations with tensor network methods. But that versions, I don't know whether it's called relativistic or not, actually. That would be
relativistic. Yes. So this Kogut-Susskind, okay, I get the point, I think. So usually, as far as I know, in the literature on lattice gauge theory, so if you accept the Schwinger model, if you really look at the Kogut-Susskind Hamiltonian, if you now try to take the continuum limit, so where the lattice spacing becomes super small, you're going to get an explosion of the cost. So you're going to require very high physical bond dimension. So you're going to have to truncate your gauge degrees of freedom at very, very large numbers to get the same precision. So you're going to get the same kind of difficulties you have for scalar field theories. However, for these theories, I don't know how to solve this issue. For scalar fields, I know now. For gauge fields, I don't know.
I see.
Probably the same ideas can be used, but I'm not sure.
Okay, yeah, that's good to know. Yeah, so I guess the interesting things maybe is that there's analogous formulation of the scalar things in the gauge theory. That would be good then, if it is like.
Yeah, I think so. I hope so.
Okay. Yeah, thanks. Okay.
Okay, are there further questions, anyone?
So I have a question about like one of the, I think like maybe even the previous transparency or like the second previous.
Yeah. This or?
Yeah. So when you talk about the Wi-Fi QFT still have fewer space but less explicit not free Fock space, like what this statement implies for Hamiltonian truncation, like in dimension.
That's a good point.
2+1 and higher.
So people are, so maybe you followed. So recently, I think it's probably, I don't remember, maybe it's Elias Miro and collaborators published something on Hamiltonian truncation in 2+1. And it's super tricky, for this reason. So as far as I understand, it still works in the free Fock space, but they add a lot of renormalization. You know, they never do direct Hamiltonian truncation. They have lots of corrections coming from perturbative renormalization. And as far as I understand, with this, for very, very small system sizes, so the system size is not much larger than the correlation length, they manage to do computations. But I have to say, these are difficult papers that I don't understand fully. They are trying to correct this issue that the free Fock space is not exactly the right one by doing subtractions.
I see. Thanks.
But this is very interesting. So I should have said that we are a tiny bit late with tensor networks. Okay, so Hamiltonian truncation people, they tried more in the continuum, at least more theories, and to solve these relativistic QFT difficulties in such a way that we can use tensor networks, the answer is probably in these papers or by these people. Because they have tried a lot to make sense of the Hamiltonian formulation of 2+1 QFT.
So one more question, Slug. Can you use such states for? I mean, can you come up with an analog of MPO using this formalism and study, say, physics at non-zero temperature, or can you also do time dependence with these sort of?
So temperature, so I see no difficulty a priori for temperature. You could write it as a purification. Okay, maybe there is a reason why it doesn't work, but that's not obvious. There could be some new divergences that I cannot think of right now. For time evolution, so I'm already optimizing with imaginary time evolution. So I could do real time. It's probably going to be much less precise. You know, like the advantage of imaginary time evolution is that you can take very large time steps. Basically, as long as the energy go down, you can increase the time steps.
Yeah, sure.
Whereas in real time, you cannot do that. So I would be limited to much smaller bond dimensions. And okay, but in principle, everything you could do with MPS, you can do with these new states.
Good. Thanks. I just want to point out that there is a question on the chat, and maybe like these people who
sorry, I didn't read the chat.
Don't have microphone or something. Yeah.
Okay, I'm trying to open the chat. Okay, the first I think we discussed, right? Is there a relation with the momentum space DMRG? I have no idea. Maybe. I think this is Herman.
Yeah.
I don't know.
Imagine you take a Hamiltonian real space, you go to momentum space, there is already diagonalized, and the entanglement entropy is 0, right? In the
yeah, I see.
So it looks like a bit like what you do, right? I mean,
yeah. The difference, Herman, is that I'm really attached to translation invariance, and that's so. In a way, this is the midpoint. The standard DMRG would be ultra local. I argue it's divergent in the continuum. This momentum space DMRG has 0 entanglement entropy, but now it's fully not translation invariant. I'm doing a middle ground where it's translation invariant. The entanglement entropy is finite.
Okay. Okay. No, it's interesting. The question where the entropy, I mean, because you are changing the basis. So you are somehow killing a lot of entanglement.
Yes.
Remaining, this is the basic. It's chain of variables in a way. It's the way.
No, exactly.
And then using the continuous MPS. This is the two things, right?
Yes.
Change the basis and using the continuum MPS. That's the trick. Okay,
yes.
It's very nice. Mm-hmm.
Yeah, and the optimization algorithm is, as far as I understand, different from what's been done, but that's big. Yeah, from a conceptual point of view, that's really the point. Yeah.
Mm-hmm. Okay. Thank you, Antoine.
Okay, if there are no further questions, then let's thank Antoine for this very nice talk.
Okay, thank you.
Okay.
Thanks, it was great.
Thank you, Michel.